So, good day students, and welcome to the third nugget in the lesson dealing with biofuels. The main theme for this nugget is fat. As you are well aware, is fat a very energy-rich substance. So fat as such is basically an excellent fuel. But to be more precise, we will concentrate on oils, vegetable oils, where they come from, and on the properties that these oils have. Some of these properties are highly unwanted. So how can such properties be eliminated by changing the chemical composition of the oil? That's the theme for now. As you remember from the first lesson, the nugget about cells, do fats, or lipids as they are called, play an important role in the living cell. The fats are to a great extent energy storages. But for that to work, it is important that the cell, when needed, can easily get access to the stored energy. So you will understand that the lipids must be relatively simple to degrade, and during that degradation will the energy be released. To make things very simple, we can say that there is solid fat, such as wax, and liquid fat, such as olive oil. Wax has been used for energy since ancient time. Wax candles have been used to provide light, and light is an energy service. And the same thing holds true for vegetable oil. Many thousand years ago were vegetable oils used as the fuel in oil lamps. Depending on where, would the oil reflect the local flora. But what we will concentrate on in this nugget are liquid fats, vegetable oils. So then, since vegetable oil has been an important fuel since millennia, why would we want to convert it? What's wrong with it? To understand that, we have to have a look into what a vegetable oil really is. A vegetable oil is not a homogeneous substance. It's a mixture. In the raw state will a vegetable oil be some 90 to 95% triglycerides, and there will be simple triglycerides and mixed, and there will be saturated and unsaturated triglycerides. There will be diglycerides and monoglycerides. The glycerides all belong to the general group of esters. They are composed of an alcohol, typically glycerol, and fatty acids. There will be free glycerol and free fatty acids, saturated and unsaturated. There will be fatty alcohols of different types. There will be phospholipids. The composition of the oil and the proportions of these components is different depending on the origin of the oil. When exposed to air, will the unsaturated fatty acids start to oxidize. Just as one example, will coffee, if stored in air, successively lose its taste if stored for a prolonged time. That is because some of the fatty acids oxidize. Another example is the rancification of lard. A third example is the drying, the hardening, or most probably the curing of linseed oil to form a solid varnish on wood. In this case, is there another mechanism too, and that is a cross-linking between the fatty acids in the triglycerides. This cross-linking binds the glycerides to each other so that the liquid oil finally solidifies. These phenomena are all more or less pronounced with most vegetable oils. So what we want to achieve by a chemical synthesis is to obtain a homogeneous product that does not readily oxidize and that definitely not solidifies in the storage tank if left for some time. To arrive at that goal, there are a few different routes that can be used. For the homework, I will want to refer you to an excellent site, namely a distance learning course at Penn State University. But let me first introduce you to what is today the most common biodiesel. That is FAME, fatty acid methyl ester. Let us first look at the name as such. A fatty acid has a carboxyl group at one end, and then there is a long chain of carbon atoms with hydrogen around them. In case the acid is saturated, is the long chain composed from CH2 groups with a methyl group CH3 at the other end. If the acid is unsaturated, there will be one or more double bonds between carbon atoms because one or more hydrogen atoms are missing. Methyl is simply the name of the functional group CH3. So it's a carbon atom with 3 hydrogen atoms around it and a free bond. An ester is an acid in which the hydrogen atom in the carboxyl functional group COOH has been substituted with the hydrocarbon group. The substitute can be most any hydrocarbon group. But if we want to have a methyl ester, we must substitute the hydrogen atom by a methyl group. Generally speaking, and from a chemical point of view, are oils and fats esters. If the fatty acids involved in the molecule are long, with many carbon atoms in them, will the melting point of the substance be high. The same thing applies if the ester contains many short fatty acids. The melting point is partly a function of the number of carbon atoms. But it is also lower for unsaturated esters than for saturated. And the more unsaturated it is, the lower the melting point. If the melting point is higher than room temperature, we call it a fat. And if the melting point is lower than room temperature, we call it an oil. So FAME is simply a fatty acid in which the hydrogen atom in the carboxyl group COOH is replaced by the methyl group CH3. But for the FAME to work as an engine fuel in practice, we have a number of further demands. There are lots of different aspects, but I do not want to go into any detail. So suffice it to say that the diesel substitute, FAME, becomes a mixture of esters with different properties. And if the amount, the fraction, of saturated and long fatty acids is too high, then will it not work as a diesel substitute at lower temperatures. However, in stationary applications, such as to replace fossil fuel oil in industrial processes, where you may have access to a heated or insulated tank, is this a minor problem. So what you have to remember is that FAME is a substitute for light fuel oil. Using the word biodiesel tends to make you think only about diesel engines. But from a climate point of view, does it not matter if you replace the use of fossil-based light fuel oil in an industry or in cars? Let us now have a look at another product, namely the hydrogenated vegetable oils, or HVO. FAME is produced using a fairly simple process. You will see that in the homework session. But the price paid is that you do not have full control of the quality. That's what I was talking about with the previous slide. The main side product is glycerol. Though glycerol is used in a lot of everyday consumer products, will there be a total overproduction if the amount of FAME expands worldwide? The production process for HVO is more complicated, but the gain is that you can control the quality in a better way. HVO can even be produced with a quality that makes it safe to be used in aeroplanes. For a high efficiency, the process needs pressures about 50 bar and temperatures about 300 degrees. The process consumes significant amounts of hydrogen gas, but there are really no problems with the side products. There are also other alternatives like ABE processes to make acetone, butanol and ethanol, and other routes are being investigated. To summarize, that is the biorefinery concept. Depending on how pure the final product is, may it find different uses. But it is important to be aware that a change of fuel in a process, though the new fuel may be presented as a substitute, may require adaptations inside the process. Just as an example, if you introduce butanol in a gasoline system, and if there are nylon packings, you might run into problems. Or if you introduce FAME into a light fuel oil systems and the temperature drops in an outdoor supply line, you may have a serious clogging. So what I want to say with this is that you should not look at this in a one-eyed kind of way. Far too many people tend to see the car engine as the one and only thing that has to be changed from fossil fuel, but that is not true. I will come back to that in the homework session.